This annual film summary details the progress and general status of the T-33A jet trainer production program during 1955. During this year, significant improvements have been made in the T-33A escape system, the cockpit area, and the tip tank fuel system. Also, as a part of this contract, a series of T-33A-5 navigational trainers have been built, and the Navy TV2s are powered with a revised engine and finished with the new standard Navy trainer paint job.
Perhaps the most significant design improvement to T-33 aircraft during this period is the integrated escape system. 8 years of operation of T-33 aircraft has shown the need for an improved system which would function more rapidly, more positively, and be more nearly automatic. The new T-33 integrated escape system enables the pilot to jettison the canopy, eject the seat, attain separation from the seat, and deploy his parachute with a minimum of preparation. If escape becomes necessary, the pilot sits in the seat with both arms on these arming levers. He sits erect with his chin tucked in and hooks his heels in the footrests. To bail out, the pilot simply raises both arming levers. This locks his shoulder harness and jettisons the canopy. He then squeezes this trigger on the right arming lever. The ejection sequence is fully automatic, and from the moment he squeezes the trigger, the pilot could be completely unconscious and still achieve a successful bailout. Of course, the escape system functions identically from both front and rear seats. And now let's take a look at some of the design details and safety features of this system. A ground safety pin is provided through the shield of the right hand grip to prevent inadvertent ground ejection. This pin is removed just prior to flight. In the down position, the trigger of the right hand grip is completely shielded so that it cannot be grasped until the arming lever is intentionally raised. Upward forces on any part of the arming levers other than the hand grips cannot raise them. The right arming lever, which jettisons the canopy and arms a seat, can only be unlocked and raised by grasping the hand grip and exerting a positive upward pull. As the right armrest is raised for ejection, an initiator is fired which provides gas pressure to the canopy thruster. As the thruster is extended, the canopy locking hooks are released, and the canopy remover initiator is fired. The system's new lap belt is designed to release automatically after the seat is ejected. A time delay feature in the belt ensures that the buckle will not release until the occupant is well clear of the airplane. Normal buckle action is similar to that of any other buckle, except that a key is provided which is retained in the buckle and starts the deployment of the automatic parachute release after seat separation. The pull of the key actuates the arming knob of the automatic release, which will deploy the parachute at any preset altitude. If bailout is made from a high altitude, this device provides a preset freefall time and delayed deployment of the parachute. For added safety, the canopy can be jettisoned without arming the seat by pulling this T-handle at the right of the seat. This assures the pilot that the seat will remain in a safe condition during and after an emergency landing. As a last resort emergency escape procedure, the pilot can eject himself through the canopy. Lockheed conducted an exhaustive test program to evolve a headrest that would minimize the possibility of pilot injury when ejecting through the canopy. Steel bands 1 1/2 inches wide mounted along the top forward edge of each seat headrest were found to be most effective. This integrated escape system, with all of its design and safety features, represents a significant improvement to T-33 series aircraft.
To meet the specifications for a trainer capable of cross-country instrument navigation in all areas equipped with low-frequency, omni-range, or ILS facilities, Lockheed produced the modified T-33A-5. All gun and ammunition provisions are removed from these trainers, and they are equipped with omni-range, glide path, and low-frequency radio compass receivers. The instrument panels were redesigned to mount two primary indicators for these systems. One indicates the relative bearing information from the radio compass and omni-range receiver, and a second indicates course error information from the omni-range receiver or the ILS glide path and runway localizer. Instrumentation is duplicated in both cockpits, and space has been provided for future installation of a distance measuring indicator for TACAN navigation. To improve cockpit lighting in the T-33A series, two systems were installed. Each instrument is evenly illuminated by individually shielded red lights, which eliminate reflection and glare at the pilot's normal eye level. Red floodlights are installed on the side of each cockpit, pointing toward instrument panels and side consoles. In addition, a white variable focus map light is provided on the right-hand sill of each cockpit. A vinyl-coated nylon fabric blind flying hood is installed over the aft cockpit for instrument training. To provide incremental positioning of the speed brakes, a thumb-operated switch was installed on the throttle handle. The speed brakes may be extended to any desired degree. The canopy and windshield defroster system has been greatly improved by using a high-pressure air system with increased airflow. Defroster air is diffused to the inside of the windshield and canopy surfaces to provide effective defrosting. The flow of defroster air is controlled by means of a manually operated valve. The heater fan auxiliary defroster system has been improved by the addition of a low-loss supply line and an improved diffuser manifold. As a design development to minimize uneven tip tank feeding, air check valves were relocated, and the fuel poppet valve was replaced with an open flow plunger in the tip tank disconnect fitting. Then, to prevent fuel vapors from entering the cockpit through the air conditioning system, a drain check valve was installed to drain any fuel from the airlines when the tip tank system is depressurized. These revisions to the tip tank system are currently being flight tested at Lockheed and are programmed for production in mid-1956. These simple modifications could be easily installed in already delivered airplanes. TV-2 Navy trainers built under this contract required the installation of a J-33A-20 engine having no emergency fuel system. The emergency fuel system switch was removed and a warning light was installed to indicate fuel pump failure. All TV-2s were painted with the Training Command's high visibility colors, International Orange and Insignia White. Anti-glare black is applied where required, and an erosion-resistant coating is applied to the rain impingement areas. Production techniques used in Lockheed's final assembly plant at Palmdale reflect the advancement in the state-of-the-art of mass producing these trainers. Parts and assemblies arrive here in carefully timed sequence to meet the demands of the fully mechanized assembly line. Here, at the head of the mechanized line, forward fuselage sections are lifted into position on the trainer's wings. Assembly begins with the mating of these major components. Operating much in the manner of an automotive assembly line, this installation has set many production records, reflecting substantial savings in time, manpower, and money. The line forms a continuous loop, and as the trainers move from station to station, assembly continues. Wheel and brake assemblies are fitted and various access doors are installed. Engines are installed, and the aft section and empennage are joined to the forward fuselage. At the end of the line, the overhead cranes pick up the assembled airplane and position it near the hangar door. It is then towed to the customer acceptance inspection area in another building. In the inspection area, each trainer is carefully examined during a final shakedown. When the inspection is completed, the plane is moved out to the flight line. Here it receives a communications check, a fuel system check, and a controls system functional check. As a final operation, the engine is started and checked out. The pilot then checks the radio on AF frequency, local frequency, and flight line central control frequency.
Palmdale Tower, runway 4, wind is east-northeast, 15, altimeter 3033 over.
During the first taxi run, he checks the brakes and throttle settings. He also checks the operation of the canopy and the pressurization of the cockpit. If all equipment functions properly, he takes off for the first production test flight. To increase flight line efficiency, all operations are monitored from this central control point. From this station, the flight line chief can communicate by intercom with any of his line crew regarding the condition and progress of each assigned airplane. And he is in constant contact with planes being test flown. For example, if the pilot finds that the airplane needs a trim tab adjustment, he radios the flight line chief, who dispatches a line crew member with proper tools and equipment.
Remote 7, this is Remote 6, over.
Remote 7, go ahead. Roger, Howard. We have 065 come in for a trim adjustment, over.
Who's the pilot, Irv?
Roger, pilot is Simpson.
Okay, I'll have him standing by.
Roger, out.
Lead man Calvert, trim adjustment for 06. Calvert, trim adjustment for 06.
The mechanic meets the pilot on the taxi strip. The trim adjustment is made on the taxi strip, with the pilot remaining in the airplane. He then takes off again for the final shakedown flight. Mechanized assembly line methods continue to increase production and reduce cost, and the equipment modifications made during this report period guarantee the delivery of more comfortable, dependable, and safe jet training airplanes.
Air Force jet aeroplanes are designed for general and combat missions. They represent a great deal of money and are key weapons in the defense of the United States. As a pilot, your first experience with jets will probably be in the T-33 trainer. But the skill you acquire in flying these trainers will be vital in terms of your future. One of the most important techniques you must learn during your training is that technique of landing the airplane. If there were no weather or other air traffic at a given field, getting down from your cruising altitude onto the runway would be no particular problem. All you'd have to know is how to fly the airplane. But when weather closes in, you have the added problem of finding the runway. However, there are various navigational and approach aids to help the pilot solve this problem. If there were no other airplanes in the vicinity of the control zone under IFR conditions, the only problem would be to land in the quickest and most economical way. The overcast would not create any great problem. The purpose of this film is to illustrate penetration and approach procedures in such a way that you can see and remember the principles that will be important when conditions are such that you can't see anything. If you learn these lessons, it'll be almost as if you can see the airfield, obstacles, and other traffic. For these reasons, definite approach procedures have been established, which must be followed. When a pilot requests clearance for an instrument approach, he must follow a prescribed flight path from his cruising altitude until he is safely on the runway. You may approach the airfield from any direction and come in on any one of the range legs. The tower will then direct you to use one of the legs for your approach, or as we shall see, may direct you to make your approach in an open quadrant. For your protection, These approach procedures have been standardized as much as possible, so that once you've learned them, you can go to any field that has these facilities in just about any weather, traffic or no traffic, request an instrument approach, and know you're going in. Naturally, there are differences from one field to another, depending upon terrain, normal traffic flow, and the available radio facilities. You'll find how these approaches vary in your Jet Pilot's Handbook. For IFR letdowns, this is your Bible. One of these should be with you in the aircraft at all times. An instrument approach has two main parts. One, penetration, which brings you from your cruising altitude down through the murk to a fix. And two, low approach, which brings you into position to get onto the runway. First, we'll consider the penetration portion of your approach. If traffic conditions at the moment require any changes from the published procedure, the approach controller will tell you so when you first report into him. There are three distinct parts or phases to every penetration. The initial penetration altitude, at which you start your penetration over the fix, the penetration turn, and the initial approach altitude. Regardless of your cruising altitude, you should make good your initial penetration altitude at the point where you pass over the fix before starting your penetration. This is nearly always 20,000 feet. As a general rule, you plan to lose 1/2 of your penetration altitude before you make your penetration turn. But this is one of the details that varies from station to station. The published chart will tell you which way to make that turn, left or right, as well as your exact headings and altitudes in all parts of the turn. You are now coming down to your initial approach altitude, which you will maintain until you again pass over the fix. When you arrive at this point, you have completed your penetration. Let's just go back over this part of the procedure again and pick up some of the fine points. On a typical cross-country, your cruising altitude will almost always be somewhat higher than your initial penetration altitude. Obviously, this means that you want to report to approach control as soon as possible, so that he can give you letdown instructions and an expected approach time. For various reasons, you naturally try to plan your flight so that you arrive over the station exactly at your initial penetration altitude, 20,000 feet. An altitude higher or lower than 20,000 feet can complicate your penetration. If you're higher than 20,000 feet, you'll have to travel much farther from your radio fix in order to get to your initial approach altitude, which not only wastes valuable time and fuel, but also brings you out over unfamiliar terrain. If you arrive at the fix below the initial penetration altitude, it may become necessary to hold or to go to your alternate. Because of the low altitude, fuel consumption is higher, and it may not be possible to hold or to reach your alternate. And finally, starting too low will bring you to your initial approach altitude too close to the station for proper clearance from any traffic over the station. Your penetration should enable you to arrive at the initial approach altitude inbound a minimum of 10 miles from the station. So begin your penetration at the published altitude, never lower. Now let's start the penetration. Generally speaking, we can classify all penetrations under two main headings. Range penetrations, which utilize oral signals throughout, and ADF penetrations, which make use of the automatic features of the radio compass. Your actual penetration will often combine these two methods. Let's take a range penetration first in an example where there's no traffic on the penetration leg. You reported to approach control about 10 minutes ago and were instructed to start your penetration at 20,000. You're coming in on the published penetration heading, orally following the beam. You hit the cone of silence, there's your fix. You're at 20,000. and want to get to the published initial approach altitude of 2,500 feet, which means that you want to be halfway down when you start your penetration turn. So when your altimeter indicates 11,250 feet, start your penetration turn. Left 45 degrees as per instructions. Then right until you're headed inbound on the penetration leg. If you've made your turn and descent properly, you hit the initial approach altitude of 2,500 feet when you're at least 10 miles from the fix. Hold this as you continue inbound until you reach the cone again. This completes your range penetration, and low approach begins. But first, let's go back to some other types of penetrations. Here's an ADF penetration. This time there's traffic on all legs and a stack 4 high over the station. The approach controller will probably give you priority over conventional aircraft, but first he has to clear the initial approach altitude. Then he clears you to start your penetration. With all that traffic below you, the approach controller will instruct you to make your penetration in an open quadrant away from the stack. Turn back inbound only when you've lost half of your penetration altitude and return to the range station at 2,500 feet. By maintaining this initial approach altitude, you will be clear of your friends up there in the stack. Again, you are over the fix, ready to begin your final approach. Here's another situation, again requiring ADF for the actual penetration, though you'll use oral signals both before and after it. This station, very obligingly, has a low-frequency homer 10 miles out on the final approach leg of the station. There's a stack over the station, but none over the homer. In that case, you'll be directed to start your penetration into the open quadrant, making good a specified track. You'll make your turn after losing half of your penetration altitude, no lower, in order to assure proper terrain clearance. Then you fly the radio compass needle to head back toward the homer at your initial approach altitude of 2,500 feet. As you hit the homer, you turn to your final approach heading, and that's all there is to it. From this point, you are ready to start your low approach. That little homer has saved you an extra 25-mile ride plus 1 procedure turn. Notice that in this case, your penetration began as usual over the range station, but ended over the homer at 2,500 feet. In this case, you have traffic between the homer and the range station, and the terrain makes it unsafe to use an open quadrant. Here is another type of penetration. Fly over the homer to start your penetration, holding your same heading, and cross the homer outbound, which tells you definitely that you're more than 10 miles out. Again, you make your letdown to initial approach altitude on ADF, making a penetration turn that will bring you back toward the homer. Cross it at 2,500 feet for final distance fix, and you're inbound to the runway, ready to begin your low approach on the final approach leg of the range. Notice in this case that although you have made your first radio fix as usual over the cone, your actual penetration began over the homer and ended over the homer. There is still another type of penetration. In this one, use the oral signals until the penetration turn is interrupted. Then switch to your ADF to return to the homer. In this situation, you have a homer 10 miles out and no other traffic holding either at the homer or on the penetration leg. You've come into the cone on your oral range and have been advised to start your penetration at station. You start your penetration, still on oral signals, letting down to half your penetration altitude. Making your penetration turn, still on oral. Then as you complete it, tune in your homer frequency and switch to ADF. You arrive over the homer on your initial approach altitude, ready for low approach. Your penetration in this case began over the cone and ended at the homer. And once again, the homer has saved you 40 or 50 gallons of Uncle Sam's very best kerosene. One thing all your penetrations must have in common. You never descend below your initial approach altitude during any part of the penetration proper. This guarantees that you have adequate clearance above any and all terrain features and other obstacles until you are safely inbound over a definite fix. Of course, the pilot's dream is to have a GCI set up at his destination. This unit can pinpoint you in space, anywhere within 75 nautical miles of the station. It'll bring you in with minimum turns, save you time and fuel, and put you in a position to make a straight-in or a GCA approach. It allows penetrations to be made much closer together. Knowing your penetration procedures well is half the battle, but the other half is pilot technique. Making IFR penetrations means 100% precision. No almosts and no maybes. As always, in flying these sensitive airplanes, a great deal of this technique will be left up to what we hopefully call the pilot's judgment. And that judgment must be exercised within well-defined procedures. Let's take airspeed as an example. Airspeed is so closely tied in with configuration that it would be impossible to standardize 1 or 2 penetration airspeeds that would suit all airplanes. Taking the T-33, we have been able to arrive at 2 penetration airspeeds, which have proven their value in almost every type of situation. We call them the low-speed penetration and the high-speed penetration. With slight modifications, you will find them useful guides to safe and efficient letdowns in just about any jet airplane you may fly. The low speed is the one you will use most, since it applies in practically all weather, except in violent turbulence. And here's the procedure for a low airspeed letdown in the T-33. 1, reduce power to 65%. 2, lower your dive flaps. When your airspeed has fallen to 196 knots, lower the landing gear. And when your airspeed reaches 175 knots, lower your wing flaps. Lower the nose of your airplane until the horizon bar is lined up approximately with the 60-degree marks on the banking index. When the airspeed drops to 150 knots, the airspeed indicator becomes the primary pitch instrument, and the vertical speed indicator becomes the supporting instrument. 1,000 feet above your initial approach altitude, you pull up the garbage, start your round out using the attitude indicator to level off at the initial approach altitude. When your penetration is going to be made through possible icing conditions, you naturally make it at a high rate of descent. In that case, you only use your dive flaps. Throughout the penetration, the heading indicator will be primary for bank during the straight parts of the maneuver, and your turn needle during turns. All turns will be at a double needle deflection unless the angle of bank required to execute it would be greater than 30 degrees, in which case you will use a single needle deflection. In leveling off from the high-speed descent, the amount of lead will always depend upon the pilot's own judgment and technique. But once again, you'll probably find that 1,000 feet of lead is about right to give you a safe level off. As soon as you've leveled off at your initial approach altitude, you reset the throttle to hold your desired approach airspeed, 175 knots. When you pass over the fix again to complete your penetration, you're ready for the low approach. Procedures for low approach on instruments are exactly the same for jets as any other airplanes. There are 5 methods of making low approaches. Range, ADF, VOR, ILS, and GCA. The local approach controller will clear you in one of these methods, depending on the weather, the traffic he has, and of course, on which facilities are available there. ILS or GCA will be used if they're available, since both these facilities, being specifically designed to aid low approaches under IFR, give glide path information. That is, they fix your position in elevation as well as your track in azimuth. As you go from the penetration phase to the low approach phase, the need for precision flying technique becomes greater. Let's put it this way. The penetration is just a method of getting you down to the initial approach altitude. The low approach is the actual getting in. The low approach is, in short, the payoff. Normally, the low approach can be considered to have 4 parts or phases. 1, the descent from initial approach altitude to procedure turn altitude. 2, the procedure turn. 3, descent from procedure turn altitude to final approach altitude. And 4, final letdown. Your procedure for the low approach will depend upon the ceiling as well as on the layout of the field. Depending on these factors, you'll use different flying speeds to bring you up to the point where you can land on the runway. In any case, as you pass through the cone, lower the dive flaps and start a descent, maintaining an airspeed of 175 knots. The idea is to get down to your procedure turn altitude in no more than 1.5 minutes. After making your procedure turn, you're in position to head for the runway. The airspeed you maintain during the low approach will be determined primarily by your configuration, and that in turn will be determined by the ceiling. When the ceiling is 1,000 feet or more over the field, you'll plan to make a normal landing. That means use your dive flaps to descend at downwind airspeed of 175 knots until you reach VFR conditions. When the ceiling is 500 to 1,000 feet, as you complete your procedure turn, drop your gear and descend at a rate of 500 feet per minute until you reach the final approach altitude at a base leg airspeed of 140 knots. Hold this until over the station. Then make a 500 foot per minute descent, maintaining the base leg airspeed until you have the field in sight and a normal landing can be accomplished. In case you have an emergency and must make an approach when the ceilings are below minimums, 500 feet, upon completion of the procedure turn, the configuration is set as for GCA final. Start a descent of 500 feet per minute until the final approach altitude and final approach airspeed is reached. Maintain this until over the station. Then start a descent at 500 feet per minute until you reach your minimums, or time from station to field is up. At this point, you should be able to land. If not, a missed approach procedure is followed. If the time from the station to the field is less than 2 minutes, the preceding procedures will be followed. If the time from station to field is more than 2 minutes, you may not desire to set up your configuration until over the station at final approach altitude. In general, the low approach pattern illustrated will apply whether you're flying on oral signals or on instruments which bring you to the runway. The instrument approach procedures illustrated in this film show principles only, not actual conditions. Actual altitudes and flying conditions will vary, but throughout your penetration and approach, you'll assure proper clearance by adhering to the published altitudes or instructions for each landing. Remembering and meticulously applying the principles shown in this film will be of greater benefit than a big, fat insurance policy.
This is the T2V-1, a two-place single-jet high-performance trainer. The purpose of this film is to familiarize you with aircraft systems and with pre-flight, normal, and emergency operating procedures. The wingspan is almost 43 feet. The fuselage length is about 36.5 feet. The height from ground line to top of vertical fin is almost 13 feet. The gross weight of the airplane is approximately 16,700 pounds. The hydraulic, fuel, and electrical systems are designed for maximum reliability and simplicity of operation. The hydraulic system operates aileron boost, boundary layer control valves, speed brakes, landing gear, arresting hook, wing slats, and furnishes power for the wheel brakes. In the event of failure of the main hydraulic system, lower the emergency landing gear control lever to the emergency position. The landing gear will extend, but cannot then be retracted. The fuel load, totaling 4,950 pounds, is carried in fixed tip tanks, in a fuselage tank aft of the cockpit, and in wing tanks. Pilot-controlled dump switches allow fuel to be dumped from the tip tanks. Fuel is force-fed from the tip tanks to the fuselage tank. It is gravity-fed to the wing tanks, then pumped directly to the engine. The entire system is fully automatic, requiring no pilot surveillance for continuous operation during flight. The major components of the DC electrical system are the generator, the battery generator switch, the annunciator panel, and the primary and secondary buses. In the event of generator failure, the generator out light will glow. DC power from the battery is removed from the secondary bus as all available battery power is diverted to the primary bus. To restore power to the secondary bus, place the battery generator switch in the bat-only position. Or, place the landing gear control in the down position. The major components of the AC instrument power system are a 250-volt ampere inverter supplying AC power to the flight instruments, a 1,500-volt ampere inverter supplying AC power to the electronic equipment, the flight instrument power supply switch, and the annunciator panel. The instrument out light on the annunciator panel indicates the failure of the 250-volt ampere inverter and the loss of power to the flight instruments. To restore power to the flight instruments, place the instrument power switch in the standby position. Instrument power will be supplied by the 1,500-volt ampere inverter. The T2V is equipped with a forced air boundary layer control system to increase low-speed stability and to lower stalling speed. When the boundary layer control switch is placed in the on position, air is bled from the engine compressor manifold and forced over the surface of the wing flaps. The flow of boundary layer control air over the upper surface of the flaps eliminates trailing edge turbulence, thereby increasing lift. Now, a selective treatment of pre-flight procedures. The first step in pre-flight procedure is the exterior inspection of the aircraft. There are several inspection points unique to the T2V-1, which must be included in the normal walk-around inspection. The T2V is equipped with leading-edge wing slats. Manually retract and extend the slats to check for freedom of movement. Check to see that the spoiler in the inboard section of each slat remains extended slightly when the slat is retracted. Ram air orifices are located in the nose of each tip tank. Check them for obstruction. Likewise, check the fuel dump outlet in the aft underside of each tip tank for obstruction. Check the boundary layer control orifice in each wing for obstruction or corrosion. Check each aft speed brake for signs of wear or improper alignment. There is a small glass port in the snubber unit of the arresting hook through which you can check the position of the snubber piston. Check to determine that all tailpipe mice are secure. The main hydraulic reservoir is located in the upper left fuselage, just aft of the cockpit. Check the sight gauge on the main hydraulic reservoir for proper fluid level. Now let's move into the front cockpit. Cockpit controls and instrumentation are grouped according to function. The left panel is devoted mainly to engine and fuel controls. The The instrument groupings include engine performance, aircraft performance, navigation, and fuel. Two components of the instrument panel are unique. The first is the annunciator warning panel. The second is the fuel quantity gauge. 9 of the most important warning indications are included in the annunciator warning panel: canopy unlatched, fuel filter out, generator out, fuel level low, engine fuel pump fail, instruments out, turn and slip out, oil pressure worn, and hydraulic pressure low. The fuel quantity gauge and indicator panel are located on the right side of the instrument panel. The fuel quantity gauge normally indicates the total weight of fuel in the inboard tanks only. Press the center switch to determine the total weight of fuel in the inboard tanks and the left tip tank. Press the lower switch to determine the total weight of fuel in the inboard tanks and the right tip tank. Press both switches simultaneously to determine the total fuel aboard. The right panel and console contain electrical, navigational, air conditioning, and lighting system controls. The following items in the pre-start cockpit check are unique to the T2V, or of sufficient importance to warrant attention. The pre-start cockpit check moves from left to right around the cockpit. Tip tank shutoff switches open with red guards down. Tip tank dump switches off with red guards down. Tip tank depressurization switch normal with red guard down. Oxygen supply valve on. Main fuel shutoff switch open with red guard down. Interphone panel settings on the center stand set as desired. Now to the right side panel. Battery generator switch off. Flight instrument power switch off. Cabin defrost switch normal. Cabin air switch on. Cabin pressure dump switch normal. Cabin temperature selector set as desired. Cabin temperature override switch on auto. Again, the previous items are not a complete pre-start cockpit check for the T2V, but merely a coverage of unique or highly important checkpoints. We move now to normal operating procedures, including starting, takeoff, stall, and landing. Starting is accomplished by air impingement on the engine compressor vanes. Wait for the crewman's signal that the air impingement hose is secure. Turn battery generator switch to BAT Gen position. Place the ignition switch in the on position. Signal the crewman to begin air impingement. When the tachometer reaches 8%, move the throttle to the ignite position, hold momentarily, then move it to the idle position at 10%. Light off should occur within 10 seconds. Prime the engine as necessary until it reaches idle speed, 38%. When the engine has stabilized at idle speed, the exhaust gas temperature should stabilize at about 550 degrees. Signal the crewman to disconnect the air impingement starter. Place the instrument power switch in the normal position. Then proceed with your post-start cockpit check before taxiing. Check RMI for alignment, which is accomplished by adjustment of the S2 compass controller. Press the annunciator panel test button. All segments of the panel should light. Press the fire detector test switch. Both the aft overheat warning light and the plenum fire warning light should go on. Press the fuel quantity indicator test button for a 0 reading. When released, the gauge needle should return to its original reading. Then, press the middle and lower buttons to check the total fuel aboard. Check communication and navigational control panels for proper settings. You are now ready to taxi the aircraft to the takeoff end of the runway. Check the annunciator panel for lights out. Check all red switch guards on the left panel for down. Go over the takeoff checklist. After takeoff clearance is obtained, move into position on the runway and hold the brakes. Advance the throttle to the fully open position. Check the tachometer for 100% RPM. Exhaust temperature should not exceed 704 degrees. Release the brakes. Use braking action for directional control up to about 50 knots. Then, use rudder control. Raise the nose wheel at about 85 knots. Fly the aircraft off the ground at about 115 knots. Raise landing gear when comfortably airborne. Raise flaps at approximately 150 knots. An unaccelerated stall will demonstrate inherent flight stability. To initiate a normal stall, slowly raise the nose of the aircraft. When the angle of attack reaches or exceeds 22 degrees, a mechanical stick shaker will warn you of the situation. To recover from the stall, release back stick pressure and apply full power. The T2V stalls and recovers with no tendency to assume unusual attitudes. The normal landing procedure is similar to that applicable to any conventional tricycle landing gear aircraft. Start your letdown to traffic pattern altitude, reduce power, and extend your speed brakes. Then lower your landing gear and your flaps when speed is below 217 knots. Fly your downwind leg about 4,500 feet abeam the runway and continue to reduce speed. Begin your 180 abeam the touchdown point, speed 140 knots. At the 90, 130 knots. Continue reducing speed and maintain a shallow glide path during the final approach. Touchdown at about 105 knots. Retract flaps when the nose wheel touches down to reduce lift and increase traction for braking. Knowledge of emergency operating procedures is a cardinal requisite for flight operation of this or any other aircraft. Ejection procedures for the T2V are similar to those prescribed for all high-performance naval aircraft. Following is a simulation of those procedures. Once the decision to eject is made, place your feet in the stirrups and sit erect in the seat, head braced against the headrest. Pull the emergency bailout bottle and disconnect the oxygen hose at the mask connection. Grasp the face curtain handle. Pull down to the full limit of travel, firing the canopy and ejecting the seat. If the canopy does not jettison, pull the auxiliary canopy jettison handle or push the canopy lock handle full forward and press the canopy open switch. If none of the above procedures jettisons the canopy, pull the canopy interlock release handle. Then pull the face curtain to the full limit of travel, ejecting the seat through the canopy. The air start is another emergency procedure with which you must be acquainted. Immediately upon flameout, move the throttle to the off position. Maximum altitude for an air start is 25,000 feet. Descend to that altitude if necessary. Then assume a glide of 200 knots. At this speed, the engine will windmill at 8 to 10% RPM. Then drain the tailpipe of residual fuel. Place the plane in a shallow dive. Move the ignition switch to on. Place the battery generator switch in the bat-only position. Move the throttle to the ignite position, hold momentarily, then slowly advance it to the idle position. Prime the engine as necessary to altitude idle RPM. Light off should occur within 15 seconds. If air starts are unsuccessful, a flame-out approach may be attempted. Here is a stylized illustration of the flame-out landing pattern, a 360-degree approach with 3 fixed checkpoints. The high key, above and outboard of the intended touchdown point. The middle key, about 5,000 feet abeam the touchdown point. And the low key. Adjust your glide path to reach the high key at an altitude of 5,000 feet. Lower gear and flaps. Simulated flameouts may be practiced by using speed brakes. Maintain approximately 150 knots throughout the approach, assuming a 2,000-pound fuel load. Pass over the middle key on your downwind leg at an altitude of 2,600 feet. Decrease altitude to pass over the low key at 1,500 feet. Try to reach the straightaway with a minimum of 600 feet. Touch down at about 120 knots. As in normal landings, retract flaps when the nose wheel touches down to reduce lift and increase traction for braking. This completes our overall review of pre-flight, normal, and emergency procedures pertinent to the T2V. Subsequent films and training will, of course, treat these procedures in specific detail.
Battalions on duty in Berlin are the mobile outposts of the American presence here. The wall is their beat. They travel as close to it as they can, keeping it always under surveillance, and keeping the forward areas of the enemy's part of the city beyond the wall under continuing observation.